Hello, everyone. Welcome to our ISD 528 interim presentation for Team 22. Our team members are Constanza de la Fuente, Inigo Perez de Gracia, Tyler Pengrel, Nolan T. Gallego, and Yue Wang. For our project, we're going to be looking at an electric pencil sharpener from a DFA perspective. Electric pencil sharpeners are used for sharpening tips of wooden pencils to a point that make them suitable for writing. They do this by using an electric motor and a set of gears to drive angled blades that remove material when the pencil's pushed in the sharpener, and those shavings fall beneath the blades into a collection area that can be removed or discarding the shavings. For our target customers and product demand, our primary customers are learning institutions with children learning to write, and secondary customers are families with children learning to write or adults that are working from home. Our annual US pencil sharpener demand is 3.4 million devices with an estimated growth of 1.9% per year, and our competition is 35 US-based electric pencil sharpener manufacturers.
Okay, so here is the exploded view of our electric pencil sharpener and the parts breakdown. As you can see, we have 20 items, sorry. So yeah, the main parts are the base, the housing, the motor, and the electric assembly, as well as the front and rear frames. And here you can see the fast diagram. So the task function that we decided was sharpen pencil. Then we have two primary basic functions that are remove material and collect waste. For remove material, we have two basic functions that are feed pencil and cut material. And to collect waste, we have catch waste and contain waste. And then for the four categories that we have, to assure dependability, we have protect fingers and prevent jamming. To assure convenience, we have minimize noise, save time, and prevent sleeping. And lastly, to enhance the product, of course, is automate sharpening. That for that we need to transfer torque and to distribute power.
We prepared two assembly sequences for this electric pencil sharpener as shown in the fishbone diagram. The build procedure moves from the left to right as assembly moves over time. In assembly sequence 1, the build starts from the base, then we add on the power supply front frame, driven gear, center cartridge, front cover, rear frame motor, and we use the motor mount strip to secure the motor. The last step after everything is to put on the housing and slide in the waste jar to finish this build. In assembly sequence 2, instead, we start the build from the front frame, then we put on the inner structure components like the driven gear, the cutter cartridge, rear frame motor, and the front cover electric assembly to complete the inner structure subassembly. After that, we put on the base and housing, slide in the waste jar to complete this build. Comparing the two sequences with the metrics listed above, we decided that sequence 2 is a better option, which makes it easier for transferring, handling, and locating the parts. Sequence 2 also better enables parallel assembly and facilitates the product family design assembly.
So in this slide, we have the functional component mapping matrix for our product. And as we can see, the functives that are done by the highest number of parts are minimizing noise, cutting material, and distributing power. And in this next slide, we have the bill of materials for our product, which has information regarding the material, the processing, the assembly, and the tooling cost for most of our pieces. And as we can see, the most expensive ones are the cutter cartridge and the large plastic pieces such as the base and the housing. So here we can see the DfM quad chart of our product. And as we can see, there are a lot of pieces that have high manufacturing cost. So when trying to optimize our product, we will have to focus on these pieces first.
Here we can see the functional differentiation table, which allows us to determine what each of our customer groups is actually going to want out of our product, right? So looking at the things that are similar to customer groups, we see almost everything we do. It's really the things that are different that we're focusing on, and those are saving time and minimizing noise. If you're in a school setting, you're probably going to want to save time. You're going to have a lot of students going in and out of that pencil sharpener, and you're going to want to minimize noise if you're ever in like a test. And then looking at our components, we see that there's actually a lot of components that we can use in order to have sort of those different functives, right? So something that could be used as our module. For the most part, those are the housing components, so the base, the housing, the front and rear panels, the front panel, the motor, as well as the actual gear train within it, and also the power supply. What we've come to is two versions, our two modules, are portable and desktop version. The portable one will target more of that family at-home market. It will be smaller and slower. Our desktop one will have that minimizing time aspect and will target more of the office or school setting. What these will have in common are their internals. It's going to be the cutter cartridge, driving system, and the melting frame are going to be shared. So that'll allow us to build that and then sort of assemble the housing around it. Here you can see our normal assembly diagram. That was assembly method 1, which we previously talked about. You can see it differentiates immediately. And that's an issue, obviously. It is going to increase our complexity as well as our cost. So we looked instead to method number 2, which we previously discussed, and you can see it differentiates much later. It differentiates after all of those internal components, only at like the housing, the power supply, as well as the waste drawer being a different size.